Yeah, so it's a big pleasure to be able to welcome Danielle Berg, Professor Danielle Berg, to today. So Danielle is an expert in all things galaxies, big, small, near, far, I believe. Did her PhD at the University of Minnesota, postdocs at University of Wisconsin, fellowship at the Ohio State University. I think I said that correctly. And is now junior faculty at the University of Texas in Austin. And so Danielle is going to tell us all about the Classy survey. And so let me just, with that, hand it over straight to you, Danielle. Thanks. Okay, go.
Thank you so much. And thanks for inviting me and having me. I've had the privilege a few times to visit Cambridge in person, and it's absolutely delightful. And I always enjoy all the conversations and the tea and all that. So, you know, I hope to visit again in person, and this just sparks more of those interactions with you all. So yeah, I'm going to tell you today about a large Hubble program that I am leading that is just getting underway scientifically, that focuses on the tools we can use with the rest frame ultraviolet. But I will just start with kind of the overview of what I was motivated, why I was motivated to do this, and go over some of the UV tools in case you have not, aren't as familiar with them as I am. So I always like to start at the beginning, something we're all comfortable with, you know, kind of this overview of cosmic time, to look at, you know, why we care about galaxy evolution. And I think one of the important and interesting points is that we do know a couple of these big key pieces along the way. You know, we've been able to identify kind of a start to our universe with the Big Bang, and we have really important detailed information from early on, from the cosmic microwave background. And then, of course, there's this really interesting period, you know, where the cosmos were permeated with neutral hydrogen and helium, where we had these cosmic dark ages. And then where my interest really starts coming in is when, you know, a few 100 million years later, we started forming these first stars and first galaxies that were emitting copious amounts of high energy UV photons, and that were able to ionize this gas and eventually completely reionize it so that we can start to see the galaxy formation. When we start to look a little bit further and we look at some of our deepest pictures of galaxies, you know, billions of years ago, something from like the Hubble Ultra Deep Field, we see these really simplistic pictures of, you know, kind of blobby, soupy looking galaxies, really simple structures that start off. And we can trace that development, you know, all the way through the peak of the star formation rate density, and somehow get to this amazing, complex universe we see today, where we have really crazy diversity of galaxies, from these, you know, giant red ellipticals to these beautiful spiral galaxies, and, you know, these kind of more crazy irregular dwarf galaxies. And so trying to piece that all together of how we got from, you know, the beginning to this is what I'm really interested in. How do we get this diversity of galaxies we see today? And, you know, studying galaxy evolution is really challenging. It's really this idea of putting together all these snapshots of galaxies through cosmic time. So, you know, as we look back more and more distant, we're kind of getting, you know, like a different, you can think of pictures of humans as they grow from babies, you know, to toddlers, to adolescents, whatnot. But now you have them of all different people, and you have to put all those pictures together to try to understand how people evolve and grow and over their lifetimes. Well, the same thing is true with galaxies. To make things a little more challenging, is that, you know, we have different tools for studying them, and they don't always go together so easily. Luckily, one of the best tools that we have that I use is just tracing the gas phase metallicity. And in a really simplistic way, this is a really beautiful tracer of how galaxies evolve, a productivity marker, if you will. So in a really simple picture, you start with neutral gas. The very first massive stars form, they create more metals, and they enrich that gas when they die. The next generation then forms with more metals in them, again, creating more heavy elements. They die, enrich the gas again. So we have this cyclic process that is stepping along in metallicity, but also stepping along in evolution to kind of give us a nice tracer for where things have happened. In addition to this, I wish things were this simple, of course, but in addition to this, we have other processes that make the picture a little bit more complex. So we also have things like accreting gas that can be much lower metallicity or more pristine. So that can come in and dilute metals. It can also trigger new star formation. Really energetic events can cause gas to flow out of our galaxies. Some of them may, float back down onto the galaxy, but some of it may escape. And so not only does this change a general metallicity, if you will, but how this actually impacts the distribution of different types of elements is still really unknown to us and a really important question for galaxy evolution. So as we've come even further, we now also use tools of really advanced simulations. They've revealed things like the large scale structure that we see, the different filaments and how galaxies form in those. But of course, computation is very intensive and expensive. And so if we want to do large scale galaxy evolution like this, it's really hard to make that evolve all the way to today, to redshift 0, where we have our very best and detailed observations of galaxies. It's much easier to only go to a redshift of 4 or 3 or 2, where things are much fuzzier. If we want to go all the way to 0, we can usually focus in on one galaxy or just a handful of galaxies. So it's hard to get both the really full picture and the local details in both. And so, like for instance, if you look at like a Hubble Space Telescope, which is a 2.4 meter mirror image of a redshift 2 galaxy with no lensing, you get some distribution information, but it makes it really challenging. But we're really on a precipice of a revolution, obviously with James Webb, but also with our ELTs that are going to be coming, where even from the ground in the near infrared, we'll really start to be able to see detailed structure within these galaxies at redshift 2 that we can much better match to the details of our simulations. And so I'm really motivated to see how can we use these observations in the future to take full advantage of this and understand galaxy evolution. Now, one of the best relationships we have for galaxies to help understand them is what's called the mass metallicity relationship. We have stellar mass here on the x-axis. And for nebular abundances, we use the oxygen abundance to trace metallicity. So we have total oxygen abundance here on the y-axis. And most of the studies we've done have been for larger galaxies, more massive, which are brighter. So something like this relationship up in the red. And then we do more detailed targeted individual galaxies that are smaller. And we sometimes have to use different types of measurements. And so it's hard to always put these giant scales of masses together to really understand how they grow and build that way. But by studying this mass metallicity relationship usually from optical spectroscopy, we get a lot of really important information. So first of all, this trend is shaped, just generally by star formation. As you form more stars, you get more massive, you create more metals, so you move up along this trend. We also see that pristine inflows can shape it because you can drive down your metallicity, but you can also, again, trigger new star formation. If we have enriched outflows, we can keep our stellar mass growing with that new formation, but not add any metals. And then observationally, empirically, we've also seen, as we would hope and expect, that it seems like this trend in the interstellar medium evolves as we look back farther in time. And so this is really, provides strong constraints on our understanding of cosmic galaxy evolution. But as you can see, lining it all up and reducing the uncertainties is really challenging. So lots of what we have done so far, mostly for galaxy evolution, has really focused on the optical. And in large part, that's because that's the easiest thing to do from the ground. We can use all of our existing telescopes to study nearby galaxies and do that. But as we want to move forward and piece everything together across cosmic time, I'm going to advocate for the ultraviolet. So in the nearby universe, this requires using space-based telescopes. Right now, that's the Hubble Space Telescope, which hopefully has a few more years in it. And then, as has been done, including by people at Cambridge, you can study galaxies that are a little bit further out, redshifts 2 to 3. You can study that same UV light from the ground because it shifts into the optical. And then using the infrared for really distant galaxies, you can do the same thing. And this is going to be a really important window to understand, again, with James Webb, and as we can get more details with ELTs, once we really focus on the ultraviolet, we can use the exact same spectra to characterize the stars and the gas for all galaxies. And so it'll make putting those pieces together much more uniform and easy for interpretation. Now, another thing that motivates this originally is that when we look at things like models of nebular emission lines, photonization models, two examples here from work by Nell Byler, looking at mappings and cloudy photonization models, and what metallicity you would measure from your standard optical emission lines, and then compared to the metallicity you would measure from ultraviolet lines. And there's a pretty good agreement between different types of photonization models and a close to one-to-one relationship, which seems really promising for using the UV lines. However, so far in practice, when we take different observations we have of both nearby galaxies as well as more distant galaxies and lensed galaxies, and we try to do that same practice of using the predictions from photonization models to get UV and optical metallicity, we find these really large scatters around these trends. And so far, we haven't been able to find any systematic way in which these are offset or vary. And so this is really telling us that we haven't really harnessed this diagnostic power well enough yet to utilize it, to really know what's happening in these galaxies from the UV lines alone. And so that's a big challenge. But again, I'm going to highlight that there's a lot of potential there. So this is just a really beautiful Muse H-alpha image of a nearby dwarf galaxy that I love to study. And then we have the near UV Hubble spectroscopic acquisition image that shows the stars in the blue here. And you can see that there's such diverse, processes happening here and information from these compact stars to this different structure in the optical emission. And what's really powerful is that from the UV, when we get that light, we can actually characterize and trace the stars, the outflowing gas, the emitting gas, all within the same spectra. So in case you've never looked at an emission line spectra, I just wanted to, in the ultraviolet, I just wanted to throw one up from a photonization model. So this is just a theoretical one, but it kind of shows you the potential of what could be available in the UV. So when it's an emission, we can get nice strong Lyman alpha, but we can also get a lot of other ions we don't usually see in other wavelength regimes like the optical. So we can get silicon 2, fine structure emission, silicon 4, oxygen 4, sulfur 4, nitrogen 4, carbon 4, our typical, helium 2 and oxygen 3, nitrogen 3. There's just, this whole suite of lines that are there that we could utilize. Now in practice, spectra have been harder to obtain and understand and interpret. But let's talk about what we do know and what's been useful so far before I show you a bunch of observations. So first, if it's an emission, Lyman alpha is the strongest, and it's a really important diagnostic because it traces the Lyman continuum. And this is because it has to escape through the same gas, it's a resonant line. And so, if you have a Lyman continuum ionizing photon that comes in, it will, do this simple thing of kicking out your electron from hydrogen, it'll ionize it, and a Lyman alpha photon will also be absorbed. So the same types of gas will be absorbed. And so if Lyman alpha is getting out, that tells us that Lyman continuum can probably get out. You've probably seen little toy models like this before. When we get things like Lyman continuum and Lyman alpha to come out, there's a couple of different main theories that we think that the ionizing photons likely escape. The first one is if we've had maybe some cleared channels that are mostly free of gas and dust, maybe by previous bursts of star formation, that then allow those photons to come out. And the other one is the idea of a density bounded nebula, where you just don't have enough gas to absorb all the photons. And this is kind of akin to some of the different cloudy days you maybe see in Cambridge sometime. Sometimes you have these streams of light coming through, or sometimes you have a more hazy day. And from Lyman alpha, because of this resonant line, it can also tell us a lot of things about the gas that are around galaxies, the geometry, the porosity of the neutral hydrogen. So you can imagine if you had a central starburst and maybe some gas around it, when that central starburst is emitting light, you're going to get photons that are absorbed along the line of sight to you, but they can be backscattered off this cloud and then shifted enough that they won't be absorbed on the front side. And so you'll get this red shifted Lyman alpha profile. And so that kind of tells you, in at least a toy model sense of, what type of structure you have. And alternatively, again, there's lots of different Lyman alpha shapes you can get, but in another simplistic case, if you have maybe more of these, channels, they don't have to be necessarily completely clear, but, maybe they're lower column density of gas or dust, you can start to get some of those photons that are able to escape towards you towards the line of sight. With the outflow, they're blue shifted a little bit, and you can also still get this backscattering, such that now your Lyman alpha profile turns into a double peaked with a blue shifted peak and a red shifted peak. I'll show you some Lyman alpha profiles later, but this is also just important to remember that all resonant transitions will kind of, behave this way, because I'm going to show you some other ones in a little bit. Now, after Lyman alpha, the next strongest lines are these other nebular emission lines we sometimes see, and they can give us some good tracers of gas conditions. So these oxygen 3 lines here, these are temperature sensitive aurora lines, so they're similar to 4363 in the optical. We also have this carbon 3 doublet, which is a density sensitive diagnostic. When we have very high ionization, we can get helium 2 and carbon 4 emission. And when we're at low metallicity and low dust conditions, we can also get silicon 3 emission, and this doublet is also density sensitive. Again, within this same gas range, all the same gas range, the far UV, we also get lots of transitions that are sensitive to ISM absorption. So again, we can start to trace the gas metallicity there, the outflows, the porosity, the column densities along the line of sight. And again, within the same wavelength regime, there's also features that are sensitive to the ionizing stellar population. So here are a couple of different features that we sometimes look at that what we're doing here is we are keeping the age constant at about 3 million years, but we're changing the metallicity, and you can see how the shape of these features change, especially the P Cygni profiles with metallicity. Some of these are also sensitive to age, but some of them are, only sensitive to one or the other. So now if we keep the metallicity constant around 20% solar and change the age from 10 to 100 million years, from 1 to 10 million years, you can really see how these things change and are really sensitive. So again, within that same range, we can characterize the emission lines, the absorbing gas, and the young ionizing stellar population that's driving them. And that's really powerful. All right, so here are 2 galaxies. In orange, this is a redshift 2 lens galaxy. In black, this is a nearby about redshift 0 galaxy. And it's just to point out that, these lines are seen across multiple redshifts, so they're going to be really great tracers. And as I've mentioned already, they can characterize a lot of things. So they can characterize the ionizing stellar populations. They can tell us about the very high energy ionizing photons. They can tell us about gas that's escaping along the line of sight, and they can give us other diagnostics for the nebular emission. But as I mentioned in the beginning, this all requires that everything is properly calibrated to what we already understand about galaxy evolution. And this is what motivated my large survey. So looking into the Hubble archive, and in particular the Cosmic Origin Spectrograph archive, which has done a lot of great science over the years, I found that most people are motivated to use it efficiently, and so would only focus on one part of the far UV depending on their scientific goals. So for instance, if people were interested in looking at Lyman alpha and maybe nearby stellar winds or particular ISM outflow lines, they would get this portion of the spectrum. If instead they were interested more in maybe these emission lines plus other stellar lines, they would get this middle portion of the far UV spectrum. And then rarely people would go after like the carbon 3 emission lines and get this portion of the spectrum. And so the archive was very piecemeal when I looked at it, despite lots and lots and lots of observations. And so the goal of this COST Legacy Archive Spectroscopic Survey Program, CLASSY, is to just unify this, so that we can use these full templates to really understand all of these properties together. And in addition, we focused on only using the highest resolution that we can and high signal to noise. And so that we can also get at some of these fainter and more resolution sensitive features, fine structure features, stellar photospheric features, and combine all of the science together within the same galaxies. So we have now collected all this data. We have these 45 galaxies, and we try to span a broad parameter space so that whatever templates we produce or whatever data you're looking at, you can find a similar galaxy in Classy, slightly representative. It's not going to be perfect, but did the best we could. And so you can see we span a broad range in star formation rate, stellar mass from 10 to the 6th all the way up past 10 to the 10th solar masses, broad range in oxygen abundance or metallicity. We also tried to expand our range of density because it's been suggested that at higher redshifts, perhaps things have higher gas densities, and that could play a role. And then also ionization parameter as characterized by oxygen 3 to oxygen 2 emission. And so as of the end of December, our survey is complete. And so Classy used a lot of archival data plus 135 new COS Hubble orbits, and went after 45 galaxies. So looking at a bunch of them here, you can see that SDSS R-band optical light is shown kind of in the red-orange, and it can be compact or more extended. But in all cases, we really tried to go after things that had really nice compact stellar clusters at their center that were driving this emission. And so that's in blue, showing you in the near UV. And this is showing the comparison between the COS and SDSS aperture. So they're very similar. We're getting similar amounts of light, so we can utilize both the UV and optical together. There are a handful of these galaxies that, like Haro 11 is too far south to have SDSS data. So we've had to get other data, IFU data, things like that. But putting that all together, it's been a complicated data set. We've actually helped the COS team improve their pipeline because we're taking lots of different gratings, different observations at different times, different settings, and trying to combine them all together. And so this has been, we've worked on this for a year with a specialist at Space Telescope to really try to do this well. And the resulting spectra that we get come out to be really beautiful. You know, our goal was to have signal to noise of 5 on average in the continuum for most of the spectrum. On the very red end, where we only really care about like the carbon-3 emission line, we didn't really care to have an important continuum over there, but for all the other parts, we wanted to be able to do the stellar absorption and emission. And we're going to put out a lot of different resolution spectra. This is a Treasury program. We're going to try to give you tools to use this, to compare to your other studies, to do new science. And so if you want just a portion of it, that'll give you the highest resolution, but we're going to create different convolved resolution data sets. They'll be out, we're hoping, in the beginning of June to go after whatever science you need. And then just to show you 2 extreme examples of the beautiful spectra we have, this one is a good example of a galaxy that has a lot of nebular emissions. So I mentioned there are ISM absorption lines in here, fine structure emission lines, stellar wind and photospheric lines. But you can see there's lots of great strong nebular emission lines in this spectrum. And on the other end of things, we also have galaxies that don't have a lot of emission, but have tons of beautiful absorption lines. So here you can see a bunch of those and everything in between. So there's a huge variety. And again, we use the highest spectral resolution that we could on HST COS. So you can hopefully get good velocity information and things like that too. All right, so we're starting to do, I've done some like pilot work with a few of these galaxies. So I want to highlight that. Here is a couple examples of some of the emission line galaxies that we have within the Classy sample. And I want to point out some of the work we can do because we have now a much bigger sample spreading parameter space with these emission lines. So I've been looking at for a while trying to study the UV carbon to oxygen abundances from some dwarf galaxies, these compact blue SDSS galaxies. In the UV, they look like this, compact stellar clusters. The COS aperture, 2.5 arcseconds. For these nearby galaxies, that's really only about half a kiloparsec in physical space. And so these are tiny galaxies, 10 to the 6th to 10 to the 8th solar masses. And these are low resolution spectra with costs, so not the high resolution stuff you're going to get from Classy, but even from that, we found lots of oxygen and carbon emission, and we're able to do science with it. Now, carbon to oxygen is something we haven't understood for a long time, even though carbon is really important, to understand all sorts of things, yields, dust, all sorts of feedback, all sorts of important things. Our theoretical expectation is that carbon is a primary element, meaning metallicity independent. And so the production of carbon to oxygen should just be dependent on the nucleosynthetic yields, and we would expect it to be constant. But starting all the way in the 90s, a lot of this work led by Don Garnett, started to find some galaxies that suggested a secondary trend. So that means it's dependent on the initial metallicity in the gas, in the stars, and it increases that way. And so it's been long debated about, is this the real one? What would cause this pseudo-secondary dependence? Could it be metallicity dependent outflows in massive winds from massive stars? Could it be the timescales that they're produced on? What is happening here? And so that sample I showed you, they were all fairly low mass galaxies. They don't have a large spread in oxygen abundance, but they do have a large spread in the carbon to oxygen abundance we measure. And so that's really challenging to understand which relationship that follows. So to put that in greater context, we can also compare to things like the disk and halo stars from the Milky Way. At very low metallicities, we can compare to the DLAs. And we can also utilize work that's been done at higher redshifts, as well as recombination lines from nearby galaxies to try to piece everything we can together about C to O. And again, you still see a lot of scatter in this trend. So what we did then was started with just some really simple chemical evolution models and looked at if we varied things like the number of bursts, how long the burst was, and how much oxygen outflowed from that burst. So we're allowing the effective yield of oxygen to vary. That for these different models, we were able to reproduce this general trend and scatter that you see. And basically, it's really sensitive then to this burst cycle. Oxygen is going to be produced very quickly in these type 2 supernovae, and then could be preferentially blown out of the galaxy, compared to carbon, which can be produced in both massive and more intermediate mass stars and come later. And so we can get this zigzaggy pattern. And that motivated us then to further look at doing chemical evolution models of individual galaxies. And so, we had lots of abundance measurements for them, their mass measurements, their star formation rates, things like that. And we could try to tweak these things just a little bit to see if we could actually reproduce these actual abundances in these galaxies. And so we have carbon to oxygen here, and it's color coded for these 10 galaxies we looked at by star formation efficiency on the top, the effective yield of oxygen in the middle, and the burst duration on the bottom. And so these trends suggest that the star formation efficiency indirectly related to both the effective yield and the burst duration. And this makes a lot of sense once you start to think about it a little bit. Efficient star formation is going to be associated with greater oxygen outflow in these low mass systems. More efficient star formation is going to deplete a greater portion of the interstellar gas by forming more stars at a higher rate. Plus, these greater number of stars are also going to drive more outflow of ambient gas. These things together are a likely reason why the burst duration time is then shorter. And when that happens, that also means that if you're, very quickly after a short burst, that also can mean then that your nitrogen, which comes from slowly evolving lower mass stars, hasn't maybe necessarily been ejected with time. So we kind of get the inverse relationship for nitrogen to oxygen. And we can also compare that to carbon to nitrogen. So it just really seems that these ratios are very sensitive, critically sensitive on the star formation history and the effective oxygen yield at low masses here. And this is further supported by looking at, just this trend loosely with the total baryonic mass of these galaxies. And so we see a scattered, but a general trend of carbon to oxygen that, is decreasing as we go to larger masses. And what that means then is that the galaxy is holding on to more of that oxygen. And in the same, looking a little bit lower, the effective yield of oxygen goes up with higher mass, again, holding on to more of that. So that it comes from our chemical evolution models and our observations. And it agrees with this loose understanding that we have from a handful of galaxies that have been observed in outflows and looked at their metal loading factors that shows that, lower mass galaxies, this is the suggestion, actually are expelling more of their metals. So this may be very important for understanding these chemical evolution pathways in the early universe and for these low mass galaxies nearby. Now, additionally, as I've mentioned in these spectra, you can also get carbon-4 and helium-2. And I just want to highlight that why this is so surprising. And I'm sure many of you know that this has been a problem long before I was ever in astronomy. People have been studying helium-2 for decades. But one of the big challenges is that if we look at the spectral energy distribution of models of AGN in gray, and then we have two stellar populations in orange and blue, where the blue one is lower metallicity, and then we look at where these lines are formed in terms of ionization energy, we see that carbon 3 to 4 is pretty high, and we can just reach it a little bit with our low metallicity stellar populations. But helium-2 is a recombination from helium-3, and that happens all the way out at 54 electron volts, and our current stellar population models just can't reach that. So we don't understand how these very tiny galaxies, metal poor galaxies, are producing these lines. Additionally, in carbon-4, if you're not used to looking at that line, it often looks like this in a lot of galaxies we observe in absorption combination here. So this is from the Megasaurus survey from Jane Rigby, using a sample of lens galaxies. This is one of their best spectrum. And the first thing you do is want to get rid of the stellar portion of this. So you fit the stellar continuum, this P Cygni profile, and you subtract it. And then you're still left with this deep absorption. We can then compare to what the theoretical absorption ratio looks like. And you see that these absorption profiles are even stronger than this theoretical ratio. So there's so much gas along the line of sight absorbing for carbon-4 that both of these are saturated. That's pretty common in a lot of galaxies we look at. So to see that pure emission is pretty special. Now, showing you how much better, for instance, Classy is, the low resolution spectra that I showed you originally are in purple, and the new high resolution spectra that we get from Classy is in black. And if I focus first on the helium-2 of two of these galaxies, the helium-2 is in black, and I'm showing you in comparison the width of the oxygen-3 UV nebular line. And you see that they have very similar widths, and they're only about 80 kilometers per second wide. And so this is really strong evidence for nebular helium-2. It's very narrow, and this is telling us that something is emitting a ton of very high energy ionizing photons. And then carbon-4, for these two galaxies, again, compared to that oxygen-3 line width, we see actually is broader and has some shape to it. And that's initially very interesting. And then we can remember that carbon-4, this doublet, is also, they're both resonant lines. So similar to Lyman alpha, they could be double peaked. And so if we fit the 1548 line with a double Gaussian, and this is the stronger line based on their theoretical emissivity ratio. So we can use this double Gaussian to predict what the 1550 line should look like. And for this particular galaxy, it's a really great fit. And so this tells us very little carbon-4 gas along the line of sight. And that's the type of gas that high energy ionizing photons are sensitive to. So this is a galaxy where very high energy ionizing photons could be escaping. On the other hand, this other galaxy, which again, still very unique to have both in emission, when we do that same process, it doesn't fit quite as well. So this is telling us that probably there's a little more absorption in this galaxy, because if you remember correctly, this 1548 line also absorbs more strongly. So still very little gas, but also some absorption going on. Now, within these UV spectra that we get for Classy, we also get these other rare, very high ionization lines that we don't see very often for some of these extreme emission line galaxies. Obviously, the higher, more mass, more metallist-rich galaxies, we don't see these so much in, but we're getting things like silicon-4 emission, some very faint sulfur-4 and oxygen-4 emission. We're getting silicon-2 star emission here. And so we're getting a lot of really nice new features that we can add to our modeling and our understanding. In addition, with these deep optical spectra that we're trying to get for all of our galaxies, for the extreme emission line ones, we're also starting to see really nice argon-4 profiles. And for this, these two galaxies in particular, we also observed iron-3, some faint iron-4, and even really nice iron-5 profiles. And this is really nice because we don't usually observe all the relevant ion species for iron. And so this allows us to try to roughly estimate the iron abundance for these galaxies. This has been a question that's kind of been opened up lately, is what is the alpha to iron ratio for galaxies, especially as we look back in time? Is this something that plays a role in how hard their ionizing spectra are? Well, so we did a very detailed chemical analysis of these two galaxies in a paper that'll be on the archive tomorrow, both with our standard, 3-zone H2 region model, but also adding an analysis with a very high ionization zone. So calculating those temperatures, densities, and metallicity separately and adding them in. And something really interesting emerged. For alpha element ratios, so oxygen, argon, neon to hydrogen, these 3 elements for each galaxy have very similar values. So for J104457, we're about 5 to 6% solar. And for J141851, we're closer to about 7–8% solar, some variation there. But for the other elements we measured, non-alpha elements, nitrogen, carbon, and iron, they're much lower. So for the first galaxy, around 2% solar, and for the second galaxy, around 3% solar. And so this would argue in the gas now that we could be seeing depleted iron to alpha, or in the opposite way, enriched alpha to iron. And of course, carbon depletes and iron significantly depletes onto dust. These galaxies are not thought to have very much dust, both due to their stellar continuum fits, their Balmer decrements comparing helium-2 in the optical and UV, and nitrogen does not deplete onto dust. So again, this isn't a closed issue, but it is very suggestive that all of these elements are very low metallicity. It's very interesting. So we dug into this a little bit further. We wanted to look at some of our photonization models. And the first thing I just want to draw your attention to is the shape in a normalized H2 region of looking at the ionization parameter, log U, as a function of radius. So for your volumed average kind of initial log U, if it's at -3, kind of initially where the photons are first hitting your gas cloud, this is the shape you get, declines with radius as you have fewer photons, makes sense. As we start to go to some higher ionization, we start to see the shape changes a little bit, especially keep your eye on the very inner portion of the H2 region. So as we start to go to very high ionization, we start to see it gets really steep in the inner portion, the very small inner portion of the H2 region. And then using a log U of -1, but changing the alpha to iron ratio. And we can do this kind of in a loose manner by making the stars very metal poor, but keeping the gas, which is dominated by the oxygen for the cooling, keeping that at the normal metallicity. If we just change that alpha to iron, we see that it gets even a little bit more compact and steep in the center, but not significantly. And so how does this affect the emission line ratios that we actually observe? Well, relative to, I'm missing an H here, but relative to H beta, the increase, for instance, in helium-2 emission that you get from an alpha to iron enriched model compared to normal can be between 10 to 40%. Whereas, things like your oxygen-2 actually declines quite a bit. So this is really interesting, and it kind of, goes in line with the results of like the Chuck Steidel group was finding. But when we use this model, it still doesn't make up for the emission, the very strong high ionization emission lines we observe in our spectra. It's not enough to completely compensate for it. So something else we're doing with CLASSI, as I've mentioned, is fitting the stellar populations. And so I have a graduate student that I started working with at Ohio State Grace Oliver, who has been working on this and has a draft nearly done. So we hope to have this out to you sometime this summer. But basically, we can use all these beautiful features in our Class E spectra to fit the stellar populations really sensitively. It's a, light-weighted average of different bursts that we can put together. And we can then use this as inputs to our photonization models to really try to fine-tune this for each galaxy to see if we can reproduce the lines with all of the conditions we measure. Now, here's the two examples of those galaxies. So one of the things that's really interesting is that starting with just really simple photonization models, and you don't need to understand all the details of these, but what I want you to see is that we're plotting ionization parameter on the x-axis. So it goes from low to very high ionization parameter. And then we're looking at the predicted emission line ratios on the y-axis for a couple of different metallicities spanning very, very low up to 30%. And then we're looking at that population of blue dwarf galaxies I showed you earlier. And what we find is that these four lines are low ionization lines, but they go in increasing order of their ionization potentials. So we have nitrogen 2, oxygen 2, sulfur 2, sulfur 3, excuse me, and argon 3. And for the most part, overall, our models do a pretty good job of encompassing the observed line ratios that we see. But as we go to higher and higher ionization, so now considering oxygen 3, argon 4, neon 3, and helium 2, we start to see that our observed points get more and more discrepant. So as I mentioned before, we've known about this helium 2 problem for decades, but it turns out it may be a bigger problem than that. Really kind of everything above like 35 eV gets more and more challenging for us. So we have a high energy photon production problem that our stellar population synthesis models currently aren't able to reproduce. So what Grace did was took these input stellar population models from these two galaxies and then said, what additional energy do I need to reproduce the observed emission lines? And this is an entire suite of UV lines now and optical lines. And the result looks something like this. So you have your best fit BPAS. So this is a binary stellar population synthesis model. In green here, and you can see how we've matched it up here to our observed UV spectrum. And you can see out here to its ionizing continuum where the helium 2 and carbon 4 are, and it just doesn't produce enough ionizing photons. And so the shape that Grace found that's able to consistently reproduce all of the emission lines, we did black bodies because they're simple, looks something like this. And so we get a pretty hot black body that peaks, really far into the blue. And so this is partially so it also doesn't disrupt all the other low ionization lines that already agreed well. And we get this combined model that looks like this purple one. And so this particular galaxy has about 60% of its luminosity that's coming from the black body. And again, it's, around, I don't remember exactly what she found for this one, somewhere around a 70 to 80,000 Kelvin black body. So very, very hot. And we don't know yet what produces these things. There's lots of ongoing work and arguments about what this could be, but we just want to put out, what these shapes actually look like so we can start getting all the models to come back to us of what these things could be and start matching them up. So if you have other ideas, I would love to hear them. And of course, we're going to have a suite of 45 galaxies like this to compare to. So it'll be a really strong constraining set. So lastly, I want to show you, just a few other highlights of Classy. So, here's this diversity of Lyman alpha profiles we're observing with Classy. Some of these had existing spectra that covered Lyman alpha, but we do have 27 new Lyman alpha spectra in the nearby universe. I love the double peaked emission ones. Those ones are exciting. So we have like 16 new really strong Lyman alpha emitters. We have 7 that are weak or kind of combination lines with a strong damped Lyman alpha profile. That's really interesting. And this allows us to now look at like all these resonant lines together for some of these galaxies. So carbon 4, silicon 4 is also resonant. And, a very simple idea would be that, gas within a galaxy is maybe generally low column density to allow these emission lines. So they all would have similar profiles. But with the diversity of Classy, we're seeing something very different. And so going back to this, one of my favorite galaxies that I showed you earlier, J104457, that had this beautiful double-peaked carbon-4 that is allowing the escape of very high energy ionizing photons. It has this broad damped Lyman alpha profile, which would be, suggestive that it's absorbing most of those lower energy ionizing photons. And so that's really, really interesting. But with the higher resolution classy spectra, it's even revealed, there it is, this tiny little baby emission, Lyman alpha emission at the bottom of this that we didn't see in the lower resolution spectrum. So this is really exciting. And again, for our pilot study, we were comparing all these emission lines, and with the well-known nearby galaxy SBS 0335-052, it's also in our sample, that allows us to look at different column densities of different kinds of gas, and motivated that for the follow-up with some GBT H1 observations, because we think some of these combination profiles could be evidence in support of the holes theory for Lyman continuum, Lyman alpha escape. And so we've got some really beautiful H1 detections and H1 masses from this. And we recently just got another program approved to do another, I think 35 of the classy galaxies, or 25 of them. I'd have to look at the details. We just got that. So we're really excited to follow this up and fill in that information. And so finally, I just want to remind you that for the future, these, everything we're going to learn from classy, again, it's a Treasury program, so we're going to release all these tools to you and this data to you this summer, and we want you to run wild with it. It's going to be really useful for shaping our future. So, as it stands, these very high redshift galaxies like this one from Taylor Hutchinson at redshift 7.5, has done heroic observing on Keck of like 16 hours to get this Lyman alpha profile and 7 hours to get this carbon-3 profile. But, with something like the Giant Magellan Telescope, we're going to be able to get similar and higher resolution emission line detections in 4 minutes. And if we do something more similar to Keck and do something like 4 hours, we're going to get, the level that we're seeing in the nearby universe. And so really having these tools to interpret and understand this is going to be so important to understand galaxy evolution all the way out into the first galaxies. So I really have no idea where I am on time, but I'm going to stop here. So I apologize if I talk too long, but just here's, kind of a suite of showing you all of our spectra and many things to come. And I would love to take questions and suggestions and anything you have.
Fantastic. Thanks, Danielle. Right on time. No problem there at all. You can't hear it, but there's raucous applause going on all across Cambridge. I will stop the recording now and we can move on properly to the Q&A session. I can already see